I want to do an introductory problem that'll get you used to some of the terminology that shows up in some of the other problems. We have a common unit used for rotations in various types of machinery is RPM, which stands for revolutions per minute. If a router, a woodworking tool, is spinning at 22,300 RPM, how many revolutions per second does it complete? Turns out this is just a unit conversion problem. That question, at least, it's 22,300, that's a comma, revolutions per minute. If I just multiply that by 1 minute over 60 seconds, okay, the minutes will divide out and I'll have revolutions per second. And I get 372 for that. Now, often we'll be talking about how many times something happens per second, and we often call that the frequency. So, for instance, a sound wave that occurs 440 times per second would be a sound frequency that we've assigned the musical letter A to. I think it's in the octave above middle C, but it could be the second octave above middle C. I can't remember. How long would it take for a single rotation? How long is a time in seconds? Okay. And it turns out we call that the period, time for one occurrence. Anyway, if this is the number of times per second it happens, the frequency ends up, or the period ends up being 1 divided by the frequency, just the reciprocal of the frequency. So in this case, the period is going to be 1 over 372. And if we have revolutions per second down there, we'll end up with seconds per revolution, because that's in the bottom of a fraction. It gets flipped and multiplied. Seconds per revolution, and that's the time for a single rotation. In this case, it ends up being 2.69 times 10 to the minus third seconds per revolution. And a way to write that is 2.69 milliseconds. In the metric system, 10 to the minus third is what we use for milli. In this case, it's a prefix to the actual unit, which is seconds, and the metric prefix is 10 to the minus third is milli. All right, now in this router, you might have a bit that has a diameter of 0.750 inches. How fast will a point on the outer edge of the bit be traveling? By the way, here's a picture of some various types of router bits. You can buy router bits for all sorts of different shapes and diameters and do all sorts of things with them. Just about anybody that has a router for any length of time will start acquiring a pretty good collection of these things. I have quite a few. First thing I want to do is convert that 0.750 inches into meters. And when I do that, I get that that's equal to 1.91 times 10 to the minus 2 meters. But that's the diameter of the thing. Okay, I want the radius. So if I just take that and divide by 2, I get 9.53 times 10 to the minus third meters, which another way of writing that would be, there's that 10 to the minus third multiplier again, 9.53 millimeters. And wherever my steel ruler is here, 9.53 millimeters would be just about the distance between my fingers on this thing here. So that's about how big it'd be. Okay, well, how fast will a point on the outer edge of the bit be traveling? Well, in 2.69 times 10 to the minus third seconds, it travels all the way around a circle. The circumference of that circle is going to be the distance it travels. And so the speed in this case will equal 2 times pi times r, that's the circumference of a circle, divided by the period of this thing. Okay. Or you can actually do it with 2 times pi times r times the frequency, because 1 over the period is the frequency. If the period is the reciprocal of the frequency is also the reciprocal of the period. So either way we could do this thing, and we just plug in our value for the radius there, and 9.53 times 10 to the minus third meters. And then I multiply by, I'll just go ahead and multiply by the frequency there. Now, a revolution is kind of a placeholder unit. It's not an actual physical unit. It's just a rotation. It doesn't have any places. So the actual only units on this thing are the seconds down there in the denominator. And you can write that as a second to the minus 1. You can think of it as just a per second if you want to. I'll write it as seconds to the minus 1. Now, we know that's on the bottom of a fraction, but when I plug this in, I end up with a speed that doesn't sound terribly impressive, 22.3 meters per second. But wait until we calculate the centripetal acceleration of this thing. That's the next question. What's the centripetal acceleration of the point on the bit? Well, centripetal acceleration, this is our first calculation of it. A equals v squared over r. V squared, that's 22. It's going to be something more than 400 for the numerator, and you're dividing by this thing that's got a 10 to the minus third on it. So let's see how this thing turns out. 22.3 meters per second squared divided by the radius in millimeter, or meters, excuse me, 5.3 times 10 to the minus third meters. And I get for an acceleration quite a fair amount here, unit-wise. I would have a little side calculation here. Meters squared per second squared on top, and I'm dividing by meters, which I can think of as meters over 1. I invert and multiply, and I get meters per second squared. So just to check to make sure I'm on the right track with units. Okay, that's a pretty big acceleration, actually. A way that we often express accelerations, not for woodworking bits, people don't care about that. They just care about the RPM and the diameter and things like that. But a way it's sometimes expressed is the number of G's. And the number of G's is something where you'd say this thing is, I'm just going to use a Greek letter here as a multiplier. It's equal to alpha times g, where that's the acceleration due to gravity. And this would just be figuring out how many times the acceleration due to gravity it is. And so alpha would equal 5.22 times 10 to the fourth meters per second squared divided by 9.81 meters per second squared on the bottom, and alpha will be a dimensionless quantity. I get about 5230 or so. So this would be, you could say that acceleration is 5,230 G's is the way that you could write that. Okay, that's just a little bit of a side thing, but some of the questions actually ask for that. So there's an introductory rotation problem about the only new physics we used in this thing was calculating the centripetal acceleration for the first time. But it was an introduction to converting from RPM into revolutions per second, and then getting the period and learning about some of that stuff, and also calculating a speed for a spinning object.